In today's video, we're going to continue our discussion of elimination reactions with E1 eliminations. Like SN1 reactions, E1 reactions require a good leaving group because the first step is the generation of a carbocation. So in this example, this bromine is going to leave and you form carbocation, in this case, a tertiary carbocation. And we're going to sprout a hydrogen. So I'm going to pick this one here. The hydrogen must be beta to the carbocation, and so we consider the carbocation itself the alpha carbon, and the carbon next to it the beta carbon. And some base, in this case, the best base in solution we have is methanol. And so methanol is going to act as our base and come and pick up that proton, and that is going to fall down to give this alkene. The whole reaction is reversible, and so every step is actually reversible. I forgot that in the first step. And so this is the major product of this reaction. But like E2 eliminations, you can get both the Zaitsev product here, and I could have chosen, say, this proton to eliminate and this would give the Hofmann product. Like E2, the Zaitsev product is the major product in an E1 elimination. If we wanted to consider the reaction coordinate diagram for this reaction, this is an exothermic reaction. And so I'm going to put my starting materials here, and they're going to go through a transition state to generate the carbocation, and then go through a second transition state to generate the products. And so if we are drawing this for the major product, we're going to put a P here. These are our products, reactants here, and this is the intermediate here. Like SM1 reactions, the rate determining step must be the carbocation formation step. So this is the rate determining step. I could label the activation energy, which is the distance between the reactants, or the difference in energy between the reactants and the transition state that generates the carbocation. There's a second transition state here that's lower in energy, that's going down towards the products. And overall, this reaction has a negative delta H, and so it's an exothermic reaction. E1s are equilibrium reactions, but if you apply heat, the equilibrium is going to lie in the direction of the products, and it will always go towards the major, most stable product, or the Zaitsev product. Some important characteristics of an E1 reaction include that they're always going to be greater than or equal to 2 steps. The first step is generally the generation of the carbocation, and then you have the elimination of the alpha hydrogen in the second step. They're first order because the rate only depends on the concentration of the alkyl halide. So the rate law is equal to some concentration or some rate constant K times the concentration of the alkyl halide. Because they go through a carbocation intermediate, protic solvents are better for this reaction. Heat favors the elimination. So if you're trying to distinguish between substitution and elimination, heat favors elimination. You don't need a nucleophile, and a weak base is okay. So in this reaction, methanol is a very weak base, but we only need a weak base because the beta proton of a carbocation is extremely acidic. Since you have to go through a carbocation, the alkyl halide leaving has to form a stable carbocation, which means tertiary, secondary, benzylic, or allylic. And the last thing I will remind you of is that E1 reactions favor the Zaitsev product. Like SN1 reactions, E1 reactions generate carbocation, and anytime a carbocation gets generated, you have to be on the lookout for a carbocation rearrangement. And so in this example, we don't actually have a halide leaving group, but we have an alcohol and a strong acid. And alcohols, in the presence of strong acids, can act as a base. And so that alcohol is going to pick up a proton from sulfuric acid, and that's going to generate protonated oxygen, which forms a very good leaving group in water. And so that water is just going to pop off and generate a secondary carbocation. From here, a couple of different things can happen. The first thing that we're going to look at is carbocation rearrangement in the ring expansion. And so I am going to take this bond here and kick up to that carbocation, and that's going to generate a six-membered ring with a carbocation in the secondary position there. If you have trouble seeing that, sometimes it can be helpful to number your carbons. So I'm going to number 1, 2, 3, 4, 5, and 6. And so the bond between carbon 2 and carbon 6 here is broken, and the electrons in that bond are used to form a bond between carbon 6 and carbon 1. And so carbon 2 is losing a pair of electrons in the bond because it's being broken. So carbon 2 is the one that I expect to have the carbocation. From here, this reaction is going to undergo a second rearrangement where this hydride pops over in a hydride shift to form another carbocation. this time the most stable tertiary carbocation here. And it's from this position that we can do some eliminations. And so we'll start with the most stable product, eliminating this hydrogen. And at this point, the best base in solution is probably the water that we generated way back in step 2. And so I'm going to use the water to pluck that proton off. And that generates an alkene in this position. We could also eliminate this proton to get that alkene. And this carbocation intermediate has 2 products that can be generated from it. The first one that would come from elimination of this proton here is the same as the product that we just generated over here. So I'm not going to redraw that. But we can get a different product that would come from the elimination of this proton to get that alkene. This carbocation can do a couple of things. We can generate an alkene from elimination of, say, that hydrogen to get a terminal alkene. We could eliminate that hydrogen to generate that alkene. And it could go down a completely different pathway where instead of doing a ring expansion, it does a hydride shift to generate that tertiary carbocation, which can generate 2 different products. The first would be the elimination of the hydrogen that I just drew in here, which is going to give you this product here. So I'm not going to redraw that. But we could also eliminate that hydrogen there, which would generate this product. So this reaction then has 1, 2, 3, 4, 5, 6 potential elimination products. But the major product is going to come from the most stable alkene generated from the quickest rearrangement. In general, ring expansions tend to be quicker than hydride shifts, and so I expect this to be the major product as the ring expansion happens fastest, and then this is a tertiary substituted or a tri-substituted alkene, which is the most substitutions you can get in this example.